So today's video is about electrical safety, and we're going to talk about using these two devices, an isolation transformer and a GFCI outlet. But before we do that, there is one most fundamental rule of dealing with electricity, and that is this: if you're at all unsure or concerned or having any misgivings about what you're doing, stop, turn everything off, and only proceed after you've figured things out or gotten help. There's actually a corollary or a second version of that rule, and that is this: no matter how careful you are, eventually something will go wrong. You might make a mistake, or there might be some sort of a fault in a piece of electrical equipment that you're not thinking of. Anyway, it is really the case of doing something wrong or encountering a fault that we're going to deal with today with these two pieces of electrical equipment that can make things a lot safer. And the isolation transformer is probably the older of the two types of devices. It's been around since I was a kid, and what its main purpose is to break the connection between the source of electrical power and ground. And that is critically important because when you zap yourself by accidentally touching something that is live, the typical return path of current is through you and then through the ground, and then working its way back into the neutral of the electrical system. By having an isolation transformer where the primary and secondary coils are not connected in any way, you make that return connection much harder. If I were to touch either one of the powered terminals of this plug on the isolation transformer, in theory there should be no way for current to go down my arm and through my body and into the ground. And that's because there is no electrical connection between the secondary coil and the primary coil. And that can make things a lot easier. And a good example of that would be if you're servicing something like this vintage American 5 radio receiver, where the chassis is actually directly attached to one or the other of the pins of the electrical outlet. And what that means is the chassis can actually be hot, 120 volts or more. So that's one case where you always should be using an isolation transformer. But even if you're doing something like testing a piece of equipment after it's been manufactured, and you're doing 100 tests a day, and you can almost do it in your sleep, and you're getting complacent, and maybe it's Friday evening and you want to go home, and somebody looks in the door and says something to you and you don't pay attention, and boom, you've suddenly touched a live 120 volt pin. Bad things can happen. It should never happen, but things like that do happen. And again, that's where a isolation transformer can help you by breaking that ground connection. The other thing that is similar is this GFCI outlet, ground fault current interrupter, and in other parts of the world it's called a residual current device, RCD, but they're really all the same thing. And what they do is they don't prevent a shock from happening, but they immediately shut off the power if they detect a shock. And the way they detect the shock is they compare the current from one of the pins of the electrical outlet to the current of the other pin in the electrical outlet. And if everything is working properly and safely, the two currents should be equal and opposite. And if they're not, it means there must be some current going somewhere else, most likely through the human's body, which is a bad thing. And it will instantly, hopefully instantly, shut off and prevent serious injury or worse from occurring. Now, neither of these things are infallible, and it's partly because different people and different circumstances can make you more or less sensitive to a particular electrical shock current. As a typical rule, things less than 1 milliamp are probably okay, and things more than 10 milliamps are starting to get seriously dangerous. And these GFCIs are, in most countries, set up to trigger somewhere between 1 and 10 milliamps. And the isolation transformer, if it's properly built, will actually prevent there being virtually any milliamps going from one end to the other. It should only be in the very low microamps. Now, even with an isolation transformer, what can go wrong? Well, remember my video about the 20 kilovolt high voltage generator? If somehow that 20 kilovolts were to end up on the windings of the isolation transformer, it could easily puncture the insulation and turn the isolation transformer into not an isolation transformer and potentially allow currents to flow through the body. So the bottom line is, if you're dealing with very high voltages, an isolation transformer is not going to help you. The other thing that can happen is, imagine you're dealing with an electrical device and that device has a chassis, and the chassis is attached in one way or another to some of the circuitry, and you are probing various parts of the chassis, some of them at pretty high voltages. And while you're touching the chassis, you accidentally touch one of those high voltage points. Well, you will get zapped, and the isolation transformer won't be able to prevent that because the current is not going through you to ground, it's going from one hand to another. And there used to be one rule that, well, what you should be doing is whenever you're probing something that's electrical, have one hand behind your back and be wearing insulating shoes. That's a great rule, but the truth is I've never seen anybody actually do it. So with these sorts of things, you do have to be aware about what their limitations are and what can go wrong. Now, you might have noticed on both these devices, I have both orange and conventionally colored sockets. And you might be wondering why that is. And the reason I've done that is because these orange sockets have isolated grounds, which are normally used to take a separate isolated ground wire right to the electrical panel without attaching to any other ground wires. And that can be both for safety in settings like hospitals or for electrical noise in places like recording studios. But in this case, I actually have the ground pins of the orange sockets disconnected. And I have them disconnected to give me the option of plugging in a 3-prong electrical plug and choosing whether it is ungrounded or grounded. Same thing applies to my isolation transformer. The reason why you might want something that is not grounded would be for an example of a device that might have a metal case or chassis. And when you're working on that device and it is protected with a GFCI, the innards of that device are still connected to the mains live wire. And by having the chassis not grounded, you can prevent the situation where you happen to be touching the chassis with your hand, grounding yourself particularly well, and then touching something live and getting a good strong zap before the GFCI has time to trigger. Same sort of thing but slightly different might happen with the isolation transformer. And in particular, if you have a device that might have a fault between some component in the device and its chassis, which is then grounded, well, now you have a connection to ground that bypasses the isolation transformer. And so you can get an electrical shock because the isolation transformer is no longer providing a complete disconnect from earth ground. So in those types of situations, after thinking about the situation and what device is under test or being experimented with or prototyped with or being tested after manufacturing, you have to decide whether the situation calls for a grounded or ungrounded connection. And what I usually do is cover up whichever set of outlets I'm not planning to use for a particular situation, so that I don't accidentally plug the device into the wrong one and give myself a false sense of security. Now, there are other situations where you would want to ground it, and that's why I've actually added this banana plug connector to my isolation transformer, so that I can in fact ground something that may not have a 3-prong grounded plug on it. And a good example was my 20 kilovolt high voltage generator, where I did want the chassis connected to ground, because what I didn't want accidentally to happen was high voltage to appear across the windings of its transformer and the isolation transformer and zap them both and produce a nice good ground connection after it destroyed the insulation. So I made sure the chassis was grounded, which to a certain extent might have in some cases reduced the safety factor in certain ways, but increased it in other ways. And that's a great example of one having to weigh the pros and cons of how you're hooking up your device under test to either a grounded isolation transformer or GFCI or an ungrounded one. So the moral of today's video is you can use either an isolation transformer or a GFCI to considerably improve safety when you're working on electrical devices. And by the way, this is not an expensive thing to do. A GFCI, whether you build it yourself or buy something that can be plugged in and is pre-made, can cost as little as 20 bucks. And an isolation transformer can cost anywhere from 100 bucks to 1,000 bucks, depending on the size. And usually the smaller ones are all you need for most electronics, because they only use a few hundred watts of power. So there's no excuse not to use something like that. And I really can't emphasize more that they should be considered in both home hobbyist labs and workplaces, and anywhere else where you might be encountering potentially live electrical terminals, and also very importantly where you might be encountering them so often or so routinely that one gets complacent, and it would be so easy to just make that one inadvertent mistake and get zapped. The other thing that I really have to emphasize here is you really need to understand the test situation to be able to use these things properly and safely. And this video is not the definitive end-all discussion on how to use devices like that. So if you are dealing with electricity and any of the higher voltage stuff in particular, please research this sort of thing and be safe. There is one thing I did want to point out if you're looking to buy an isolation transformer, and that is there are actually two types that are commonly available. In particular, if you look on places like Amazon, you'll see ones that are intended for audiophiles And that sort of application, where the whole purpose of the transformer is to try and minimize electrical noise from the mains going to whatever device you're trying to run. And those transformers typically have the neutrals connected together, so they're not really isolation transformers, and they're no good for the type of safety application we're looking at. Usually a good place to look are electrical suppliers, like on DigiKey here. And if you look at the specs, you will see often a circuit diagram showing that the windings are completely isolated and some sort of indication that it is in fact meeting a particular isolation standard. Some of them are even rated to a higher standard meant for hospital use or other medical type uses where you really have to be sure about the low currents because you don't want to accidentally zap anybody. So if you are looking for isolation transformers, be very careful that you get the right one, and it might even be good to, when you get it, doing some simple testing, which we can perhaps do in another video, to confirm that it is in fact isolating and isn't one of the ones meant to condition electrical power supplies without actually providing true isolation.